Welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is the first in the second section on work, energy and power and focuses on the definition of power. Well, the hard way to dig a hole is with a shovel. The easy way is to use a JCB, and that's because a JCB is much more powerful. Well, what do we mean by power? There are various things we can say. First of all, the standard definition is that power is the rate at which work is done. That's the basic idea. Now, as such, it's a scalar quantity, and so is time. So power, because work is a scalar, and so is time, and so power must also be a scalar, and the SI unit, Système International, is the watt. But a watt is but a joule second. In other words, a watt is the power produced when 1 joule of work is done in 1 second. The watt, though, is not of much practical use. If you think of a microwave in a kitchen, it's 900 watts usually, or something like that. An electric kettle is 3 kilowatts. You'd be thinking of a diesel engine for a bus as being 150 or 200 kilowatts. So you want a kilowatt, which is 1,000 watts, as a unit which is much more user-friendly, if you like. So 1 kilowatt is 1,000 watts, and if we meet contexts in which power is specified in kilowatts, we need to be aware that it needs to be converted to watts in order to use the formulae correctly. Right, power is the rate at which work is done, which leads us to this rough and ready definition. The trouble with this is it really rather assumes that power is a constant. You can measure the work done over a period of time and divide it by that time. Well, you can concede that it will be an average at least, but our initial interpretations will take power as constant in order to get an understanding of how it all works. So we need to be cautious, a bit like Suvat, that when we're only dealing at the moment with constant power. So find the average power of a lift that carries a load of 2,000 kilograms when full upwards through 30 meters in 20 seconds. Force diagram first. Now the speed is constant, so that means to say that there must be a force balance. So if we know the weight, 2000 G, we must also know the upward pulling force, it's 2000 G as well. And 1.5 comes from saying 30 meters in 20 seconds. So how can we calculate the work done? Well, we need to say that it's the weight times the height, since the upward pulling force and the weight are the same. So the rate at which the work is done will be the rate at which potential energy is created. So that's the 2000 times the 9.8 times 30, that's force times distance moved. And that gives us that answer, a big number already. So if we want the average power, we need to divide that by 20, and that will give us the answer to 29,400 in joules. So we express that in context as 29.4 kilowatts. Now notice that implicit in here is a calculation where you've multiplied by the 30 for the 30 meters and you've divided by 20. So implicit in there is the speed, and in fact the force is 2000 times 9.8. So that has the form of the force times the speed. We shall have occasion to come back to that in a later video. But for the present time, we've worked out the work done and divided it by the time to get the power. Now let's look at a more complex problem. We've got a mass of 180 kilograms. It's moving up a rough slope, so there'll be a resistance which is specified as 450 newtons, and there must be a force pulling it, and we're interested in what the power of that force is. So it's the power of the force, the rate at which it does work, rather than the value of the force that's the immediate focus of attention. There'll also be a normal reaction force. That needs to be put in, otherwise our notional crate would be going straight towards down the vertical. But, as has happened in previous problems, we see that the displacement is at right angles to the action of the reaction force, and that means it doesn't contribute any work. So again we have a paradox, a force which is absolutely essential to the description of the situation but which doesn't contribute any work. So when we're dealing with work energy we can discount that. So we have three forces which we have to count, and again if we use potential energy and therefore use the work energy principle, we can stop worrying about the weight as well. Well, we'll see how that goes. So here we have our force set up. In order to do the calculation of work done over time, we'll need to know what the distances are, and that means we'll need to do some basic calculations involving speed and time. So if we've got 30 seconds and a speed of 1.2 meters per second, we'll have travelled 36 meters. Now that's the distance up the slope, and that will be essential to work out the work done by the friction and by the tractive force. But if we want the potential energy, we need the vertical height. So using the 36 as the hypotenuse and the sine, we'll get that h is 36 sine 30, and if you are on the ball with your trig ratios, you'll know that that's 36 times a half. So the height risen vertically is 18 meters. So now we go into finding the work done by the winch, and for that purpose we're going to use the work energy principle, saying that the work done by the force T, that's what we're interested in, and the work done by friction will equal the potential energy gained. So if we express, there's our picture which is telling us how that all comes about. The figures work out like this. We're going to have 36t because this distance is 36 and the force is t, so that's the work done by the force. It'll be minus 450 because the 450 is pointing in the opposite direction, times the distance 36, and that will equal the potential energy gained, which is 180 g plus times 18. So if we make our 36t, that's what we're interested in. Remember I said we were interested in the 36t rather than the t itself because that's the work done. We have this calculation to do. Putting the numbers in, we get 47952. So we can now work out the average power. That's the average rate at which the 36t is achieved. So it's the quantity divided by the time, which works out at 1598.4 exactly, but I've given it, since it doesn't correspond to the accuracy we've got in G, as only three significant figures. So our answer in context is 1600 watts, and I suppose you might well say I ought to have said 1.6 kilowatts, which it certainly is the same as. So there's our final answer to the calculation about the average power. Well, that brings this video to the end, and the next in the same series will be relating power, force and velocity. I've already hinted at that in this presentation. I hope to be with you later to explore that.